Um, all right, so we've made this definition, the natural logarithm. ln of x is the definite integral from 1 to x of 1 over t dt, and I should say x must be positive. Okay. And we've been talking about this probably more than you would have liked, but we've been looking at this yesterday and Tuesday, and we know that, well, the domain of the natural log function is positive numbers. We know that it's increasing when x is greater than 1. The natural log of x is greater than 0. If it's equal to 1, the natural log of x is equal to 0. And for a positive number between 0 and 1, the natural log of x is less than 1. From the fundamental theorem, it follows that the derivative of ln of x is 1 over x. And then the second derivative is minus 1 over x squared. And since that second derivative, well, first derivative is always positive, we found out that this was increasing even before we knew that. Second derivative is always negative, so ln of x is concave down. And we also proved this. We were in the process of proving that this, I've been calling it the natural log function of the natural logarithm, proving that it really is a logarithm function. And one of those properties that any logarithm function must have is that the natural log of x times y, when x and y are positive, is equal to the log of x plus the log of y. Somebody entered the waiting room, so I'm going to let them in. Okay, so we proved that, and we had started proving okay, I should check. Can you all hear me? And can you see my screen?
Yes, ma'am.
Okay, great. We started proving this property, that the natural log of a number raised to a power is r ln of a, okay? And in fact, let's see, well, a has to be positive, of course. We showed that this is true for r an integer, but I believe that's where we ended up. So for any integer, this rule holds. Okay. Well, let's go to ln of a, I was calling it x yesterday, so I'll call it x today. Ln of x to the r is r ln of x for r a rational number. Oh, does anybody remember what a rational number is?
Is it a fraction?
Yeah. Okay. It's a fraction. It's a quotient of two integers. Means r is equal to p over q, where p and q are integers. And I can also assume that q is greater than 0. Okay. If I want to make it a negative number, I just make the p be negative. Yeah, any number that can be represented as a quotient of two integers integers is what you call a rational number. Well, there are an infinite number of rational numbers, and there is also an infinite number of irrational numbers, that is, numbers that are not rational. It really blew my mind when I found out that there are more irrational numbers than rational numbers. So there's more than one kind of infinity. Now, but anyway, that's beside the point. Okay, so we're going to prove this for the rational numbers. And to do that, so I'm going to look first, show that ln of x, oh, somebody else wants in. Okay, first show that ln of x to the 1 over q is equal to 1 over ln of x. Okay, once I have this, the rest is easy. And I'm going to kind of go in through the back door again. Note that x to the 1 over q raised to the q power is x to the 1 over q times q is x to the 1. Somebody needs to mute their microphone.
Oops, sorry, I thought I did.
Okay, so yeah, I'm going to use this algebra fact. Well, then ln of x to the is equal to ln of x. Okay, this is true, so this is true. But, okay, what have I already done? Now, q is an integer. Oh, I should say that. Q is a positive integer. Okay. Well, I've already shown that this rule works for the positive, for all the integers, in fact. Okay. So I can bring this q down. Q ln of x to the 1 over q is equal to ln of x. Okay. And this is because q is a positive integer. And we already proved that the rule holds in that situation. Okay, but that means that if I multiply both sides of this equation by 1 over q, I'll have ln of x to the 1 over q is equal to 1 over q ln of x. Okay, so the rule works for 1 over q. Okay, if the rule works for 1 over q, now let's consider ln of x to the p over q. So, and again, p is an integer, positive or negative. Q is a positive integer. But x to the p over q is equal to x to the 1 over q raised to the p power. This is one of your rules of algebra. Okay, and that means that ln of x to the p over q is equal to ln of x to the 1 over q all raised to the p power. P is an integer, we already proved that the rule works for integers, so I can pull that p down. Sorry, my lawn guys are here. That's what all the noise in the background is. They'll be gone in a minute. I know my neighbors probably love it that these guys show up at 7:30 in the morning, but anyway. Okay, so pull the P down. We're allowed to do that. But we just proved in the previous step that we can pull the 1 over Q down too. Okay, so this is P times 1 over Q times ln of x, which is P over Q times ln of x. And that proves it. The rule works. The rule ln of x to the r is r ln of x for r a rational number it works. Okay, so it's a real rule. Now, it's actually true. Okay, so fact, ln of x to the r is r ln of x for x positive r any number, so rational or irrational. But as I told you, making the step from rational to irrational a little beyond us at this point. You really need to know some more mathematics before you can understand a proof of that. But we're just going to accept that then. And we proved it for a lot of numbers. Okay, so now we have the algebra rules. Let's see, we proved 2 of them. Okay, and you have to have x and y greater than 0 are a real number. 1, ln of x times y is ln of x plus ln of y. We proved that one. 2, ln of x to the r is r ln of x. Well, we proved it for rational numbers, but it's true. It's true for all real numbers. And there is one more, which is now going to be easy to do. Ln of x over y is ln of x minus ln of y. Okay. And yeah, let me show you this last one. Well, ln of x over y, that's equal to ln of x times 1 over y. And that's equal to, okay, so I can think of x over y as being a product of 2 numbers. Product of x with 1 over y. Well, that's equal to, because of rule number 1 up there, okay, that's equal to ln of x plus ln of 1 over y. Well, that's equal to ln of x plus ln. Well, 1 over y is the same thing as y to the minus 1. And because of rule 2, I can bring the minus 1 down. So that's ln of x minus ln of y. And that proves that one. So we have shown pretty much that all three of these rules hold for this function. So it really is a logarithm function, okay? What logarithms do, they turn products into sums. Well, a product is not equal to a sum, but you can apply this function and turn it into one without violating rules. Oh, these guys are really noisy. Can you all hear me?
Yes, ma'am.
Yes, ma'am.
Okay, good. Oh no, sometimes they take longer than others.
I actually can't hear anything other than you. I don't know what you're talking about.
Okay, well that's good. Well, there's a ton of lawnmowers outside my house. They swoop in with their two lawnmowers and all their leaf blowers, and it sounds really noisy to me here, but I'm glad you can't hear it. All right. Okay, so we've got these algebra rules proved. Well, now, okay, and I was trying to do this yesterday before I did the algebra rules, and I actually need the algebra rules to do it. I'm going to show you that. Okay. Let's see. ln of 1 is 0. ln is negative for the numbers between 0 and 1, positive for numbers greater than 1. It's concave down, it's increasing. I'm going to show you that there is no big number m up here, such that, well, it's a horizontal asymptote, okay? No such number exists. That is, every m, you put a horizontal line at that height, it's going to cross this curve. So there's no number that's above the entire curve on the y-axis. And so let's see. Suppose m is greater than 0. And I'm thinking m is greater than 0 and m is big, okay? Then consider ln of 2 to the 2m, okay? Now let me put another step in. Okay, then 2m is bigger than 0 too. So in fact, that's even bigger than m. And we want to consider ln of 2 raised to the 2m. Well, from the algebra rules we just proved, I can bring that 2m down. And we proved also that ln of 2 was bigger than a half. So that's 2 times m times a half, and that's equal to m. So ln of this number is bigger than that number m. That means that no matter how high I try to draw my horizontal line, it's still going to cross that log curve. So it increases forever, okay? So therefore, the limit as x goes to infinity of ln of x is plus infinity. Okay, I've been doing a lot of talking and talking pretty fast. Questions, anybody?
No, ma'am.
Okay. Okay, well, it's also true that the limit as x goes to 0 from the right is minus infinity, and for pretty much the same reason. Okay, so this curve goes up forever, no horizontal asymptotes, and the negative y-axis is a vertical asymptote. And why? Well, what if I consider 2 to the minus 2m? Then ln of 2 to the minus 2m is, okay, you can bring that minus 2m down. And that's less than, okay, ln of 2, we proved that ln of 2 was between 1/2 and 3/4. So okay, this is going to be less than. Yeah, okay, because of the minus, flipping the inequality. So no matter how low I go here, any horizontal line through a number there is also going to cross the curve. All right, so this is, we have the limit as x approaches infinity of the natural log of x is plus infinity, and the limit as x approaches 0 from the right of ln of x is minus infinity. So we have a vertical asymptote, the negative y-axis. Or in other words, x equal to 0. And why don't I put my grids up? Okay. So picture it comes up, it crosses, and it goes up, up, up forever. Okay. So this is going down, this goes up forever. And that pretty much gives us all the properties of this function. Well, maybe it's saying that's too strong a statement, but we know a lot about it at this point. Okay. And one thing we know, okay, it's 1-to-1. Because it's increasing over its entire domain. Any function that's either increasing over its entire domain or decreasing over its entire domain is automatically 1-to-1. And that means it has an inverse. And let's see, the way you get the inverse, we're going to talk about its inverse now. Okay, there's the diagonal line. What you do is to take your curve and you flip the ordered pairs. So let's see. We're going to name exp of x. That's our name, which, okay, stands for exponential. So we're naming the inverse of x this function. And, okay, so if we take the set of all points x, y, such that y is the natural log of x, and we just flip those ordered pairs, okay, we get the inverse. This gives ln. If we flip the ordered pairs, so it's a set of all points yx such that y is ln of x. This gives the exponential. And geometrically, that means we are going to reflect the graph of the natural log about the diagonal line. Okay, so just think of taking this curve and picking it up off the sheet and rotating until it's back on the sheet on the other side of the diagonal line. If 1, 0 is on the natural log function, 0, 1 is on the exponential function. And also because the domain of ln is the positive numbers, that means the range of exp is the positive numbers. The domain of ln for the inverse is the range. Likewise, the range of ln, which is all the real numbers, is all the reals. That means the domain of exp is all the reals. That just comes because you're flipping your ordered pairs, okay? And also, we have a vertical asymptote for the natural log function at x equal to 0. Once I rotate about or reflect about the diagonal line, that means that the negative x-axis is going to be a horizontal asymptote for exp. And since the natural log goes off to infinity as x goes to infinity, well, that's going to mean exp goes to infinity too as x goes to infinity. So that's a picture of exp. And that's just from knowing that this function is the inverse of the natural log function. Questions? Are you all still there?
Yes, ma'am.
Okay, good. I long for the days when I look out over the room and see all of you. I really miss that. Okay. All right, so we know some things about this new function already. Let's see. 1 its domain, all the reals, and its range, positive reals. E to the 0 is, oops, oops. I haven't said anything about E yet. I will in a minute. Okay. So EXP of 0 is 1. That's the only thing we know for sure at this point. The limit as x approaches minus infinity of EXP of x is 0. And the limit as x approaches infinity of EXP of x is plus infinity. Also, let's see. Well, there's a theorem about inverse functions and how they're related to the derivative of the function itself. But I've never talked about that, so I'm not going to use it here. Okay. Well, that's what we know so far, I think. Okay. Well, it's increasing. We know that for sure. But that's because the log is increasing. ln, its inverse is increasing. Also, it's defined to be the inverse of the log function. So we automatically know, inverse functions undo each other. So the exponential of the log of x is x. And here, because we're taking the log of x, x has to be greater than 0. And also ln of the exponential of x is x. And that's x is any real number. Okay. So we know those things. All right. But I just wrote down this letter E. Okay, let me tell you what that is. We have shown that the range of the log function is all the reals. Okay. Let me draw the log function again. My x-axis tilted up there kind of, but okay, let's leave it. Log function, there's one right there. Comes up, goes off to infinity. Okay. Okay, so it looks something like that. But since the range is all the reals, I'm going to look at one on the y-axis. Okay. And I'm going to put a horizontal line through that one. Well, that horizontal line's got to intersect the graph of the log function. Has to intersect that curve. Because one is in the range of the log function. And that means that there's some number, and that number is named E. There is some number since the range of the natural log function is all the reals, there is some number E such that ln of e is 1. And, well, you could use the intermediate value theorem to prove this, okay? 2. Okay, so there's this number e such that ln of e is 1. E then, well, we know that ln of 2, we actually proved that ln of 2 was less than 3/4 and greater than 1/2. That means if this number has the natural log equal to 1, ln of 2 is less than ln of e. Okay, so 2 is less than e. In fact, well, e is irrational. All the really interesting numbers are. It's approximately 2.718. That's, yeah, so it's pi is irrational, e is also irrational. Okay. Questions?
No, ma'am.
Okay. Okay, well, let's see. We have, let me change back to black. Okay. We spent a lot of time now talking about the natural log function. And now we have its inverse function, exp of x. And we have this, okay, not only is there a number such that ln of e is equal to 1, there's only one number because the natural log function is increasing, okay? It passes through the height of 1 and just keeps on going up. So this number e is unique. Also, we know that ln of e to the r, where e is a special number. It's like pi in a way. Okay, when I write e, I mean this number. So I won't use anything else. I won't call anything else e. This is equal to r ln of e from the rule we proved. At least we proved it for the rational numbers, r, okay? It's true for all real numbers. But ln of e is equal to 1. So ln of e to the r is r. And I know that e xp of 0 is 1 because ln of 1 is 0. exp of 1 is e because ln of e is 1, okay? And basically just flipping those ordered pairs. So what that means is that, okay, if I look at this line and I apply the exp function to this and to this, but okay, now I did the natural log, and then I did the exponential function. I applied the natural log function to e to the r, and then I applied the exponential function. These functions are inverses of each other. So one undoes the other. So that says that e to the r is exp of r. So the inverse is, okay, of inverse of the natural log function is the function e raised to a power. That's kind of wild. And you'll usually, yeah, the exponential function, you'll either see it written this way or we'll also write it this way, okay? Usually, if what's in the exponent gets really complicated, it's nice to represent it this way so you don't have that big mess in the exponent. But people also just use e to the r. E's a very special number. Okay, so we have a new function. E to the x, same thing as exp of x. That's the inverse of the natural log function. So, okay, that means that e to the x is y if and only if ln of y is x. What's the derivative of this function? Well, I'm going to use the fact that its inverse, what's the time? 8:45. Okay. What is the derivative of e to the x? Okay, I do know that e to the x is continuous. Let's see. And differentiable. Just because its inverse function is continuous and differentiable. And we also know it's increasing. So let's figure this out. And I can use the fact that e to the x is y is the same thing as saying that ln of y is x. I'm going to differentiate implicitly here, okay? Yeah. And so I'm thinking of y as being my function. So I'm going to find dy dx. I've got ln of y is x. Okay. Differentiating. I hope you remember doing this. It seems like it was ages ago now. But the derivative of x with respect to x is just 1. The derivative of ln of y, well, that's a composite function. Y is a function, and we have natural log of that function. So I have to use the chain rule over on the left-hand side. So 1 over y, that's because of the log, but then it must be multiplied by dy dx, okay, chain rule. And that says that dy dx, multiplying both sides by y, is y. So but y is e to the x. This function is its own derivative. Actually, and in fact, okay, if you consider any constant times e to the x, that's also its own derivative. But those are the only functions that have that property. Let's see. Questions? Y'all are so quiet. Are you still there?
Yes, ma'am.
Oh, good. I think that this part of the course is such beautiful mathematics. And probably to you, it just sounds like I'm droning on and on. But okay. Okay, so this function is its own derivative. Oh, yeah. And also, all the, since this really is an exponential function, it really is a number, and then you let the exponent vary. The rules of algebra must be applied to it, right? That is that we have this rule, let's see, a to the r times a to the s is a to the r plus s. So this is one of the algebra rules. So this has got to apply to this. So e to the r times e to the s has to be equal to e to the r plus s. Because this rule applies for any a greater than 0. But let me show you that it does work. If I take ln of e to the r times e to the s, well, that's equal to ln of e to the r plus ln of e to the s. And that's r plus s, and also ln of e to the r plus s by the rule we just finished proving today. Bring the r plus s down. Okay, and I left a step out here in the previous thing. Let me put it in. So bringing the r down, I've got r ln of e plus s ln of e, but ln of e is 1. So that's r plus s. So the natural log of e to the r times e to the s is the same thing as the natural log of e to the r plus s. Therefore, e to the r plus s is equal to e to the r times e to the s because the natural log function is 1 to 1. Okay. So this is true, which had better be the case because this rule is supposed to apply to all positive numbers a and real numbers r and s. Likewise, the other algebra rules also follow from this definition. So everything fits properly in its little place. All the rules are satisfied. And we have this new function. Let's see. Most of you will probably take differential equations at some point, probably in the next couple of semesters. Exponentials, sines and cosines, they are all over the place in the solutions of differential equations. So these functions are really important. The sines and the cosines, they describe periodic behavior. And exponentials and logs describe, well, exponential growth. Okay. And yeah, so it's a different aspect, certainly not periodic, but these functions are really important in physical applications. And they come up a whole lot. Okay, let's see. What else do I need to say here? Well, I'm out of time for one thing. Okay, I'm totally out of time. Okay, so I'm going to end class. You can leave if you need to, or if you want to hang around and ask a question, that'd be okay too. I'll be talking about other bases tomorrow. Okay, but we now got the log function and we got the exponential function.
Have a good day.
You too.